Okay, this is the Chapter 6, Amines and Amides, Part 1, commentary. So we're going to continue on. In this case, we'll start off with the physical properties of pure substances. So in this example, oops, let's go back one. In this example, we have a general statement where primary and secondary amines can form hydrogen bonds. So, for example, we have a pure substance of a primary amine, and basically the hydrogen from one of the amines, notice how the hydrogen is directly attached to the nitrogen, is going to hydrogen bond to the lone pair of the nitrogen of the other amine. Now, I've never made it a requirement for you to draw the lone pairs, but this is why it makes it a little bit easier, because then you can visualize if there's a lone pair present, then you can have a potential hydrogen bond, provided there's another hydrogen attached to a nearby nitrogen, oxygen, or fluorine. For the pure substance, again, we're looking at hydrogen bonding between like molecules. So if I were to sit there and give you a tertiary amine, so in this case right here, here's a tertiary amine, and that's a carbon right there. And then here is another nitrogen. Notice on this one, there is no hydrogen bonding that can occur because there is no hydrogen on a nitrogen, oxygen, or fluorine. So the best that this could be is actually going to be dipole. Why? Because nitrogen's more electronegative than each of the carbons. So you're going to have pulling in, and then you'll have an overall dipole present here. You'll have an overall dipole on the other one. So as a pure substance for tertiary, it has to be dipole-dipole. Let's go back to the slides. Now, what happens if we have a amine that's soluble in water? Oh, go figure. Why? Because it's polar. But the big thing I want to point out to you is the minute you put it in water, it's now a mixture. So let's go back to our intermolecular forces with mixtures. On the left-hand side, we have a primary amine, and the dominant intermolecular force is going to be hydrogen bond. If you have a secondary amine, the dominant intermolecular force, again, is going to be hydrogen bond. Now, this is the tricky part. With a tertiary amine, provided it's a mixture, it's going to be hydrogen bonding. Why? Because the tertiary amine, although it doesn't have a hydrogen directly attached, it does have a lone pair. So if there's a nearby hydrogen on a nitrogen, oxygen, or fluorine, and water completes the requirement, there's a hydrogen directly attached to an oxygen, then yes, you can have hydrogen bonding. Now, it turns out that you can have actual chemical reactions with water. So it turns out, let me say that again, amines can have chemical reactions with water. Not all of them will do this, just a few of them. But what will happen is, if I were to sit there and break up water into an easier form like this, the hydrogen would go ahead and attach to the lone pair on the amine. Consequently, it would form a positively charged ion, and the special name for this positively charged ion is called a ammonium. So here are more examples down here. In this case, we have, well, the common name methylamine. The UPAC would be 1-aminomethane. Here we have methylamine and water, and it's easier if you visualize it like this. And the hydrogen is going to come off the water and bond to the lone pair, covalent bond to the lone pair on the amine, forming the ammonium. The remaining section of the water is going to form a hydroxide. So we call this a Bronsted base, aka Bronsted-Lowry base, because it accepts hydrogens, in this case from the nearby water molecules. Again, not all the amines do this, but some do. Consequently, in this form right here, the dominant intermolecular force in this case is going to be ionic. So here's another example down below. For these type of reactions, make sure to memorize these. I don't get crazy with these. I will, however, expect you to memorize the product sketch as well as the name. So the sketch as well as the name. Here's a scenario where instead of having water present, we have an acid. The same thing is going to happen. The amine is going to go ahead and combine with the hydrogen, forming an ammonium ion. However, the remaining chloride is actually not going to wither away, and it's going to actually bond to the remaining portion of the positive ammonium ion. So it'll create what's called a amine salt, an amine salt. So in this case right here, we have, again, the amine. The hydrogen is going to go ahead and come together, and when it forms a positive ion, the chloride ion is also going to stick with it, forming a amine salt. Here we have a nice example down here. The hydrogen is going to go ahead and form the ammonium. The chloride, in its negative form, will actually stick with it, forming the amine salt. The common name for this example is methyl ammonium chloride. Again, memorize. Coming down here, ethylamine plus acetic acid forms a ethyl ammonium acetate. So here's another example of salts that can form from sulfuric, nitric, phosphoric, and carboxylic acids. So it's something that we usually see with salts. It's only specific acids that may not do this, which we may or may not talk about in the future. But in general, whenever you have an acid and an amine, it will always form the amine salt. Please go ahead and scratch this out, though. I'm not going to be testing you on any reactions or on this down here. You will have to, however, know this overall reaction. Going to ISIS really quick. Here is a mixture right here. What I just tried to highlight. I'll go ahead and I'll use my lasso. So here's my lasso. Let's go ahead and take a look at those. Those are all mixtures. In this case, if I have a primary amine mixed with water, it'll hydrogen bond. Now, as I mentioned earlier, the amine may react with water, forming the ammonium ion, in which case when it's mixed with water, the dominant intermolecular force is going to be ionic. So some of those will remain as amines, other one will form the ammonium ions. And whichever one I give you, then you'll have to predict its dominant intermolecular force. Secondary is going to be hydrogen bond. Tertiary will be hydrogen bonding. I know the bottom one's a little bit tricky. Again, the reason it's tertiary is because it's going to be, the reason it's tertiary is because I'm sorry, the reason it's hydrogen bonding is because of the lone pair on the nitrogen. All right, so let's go ahead and scroll down. Here are the various types of intermolecular forces. And I do want to point out on this one, and I don't know why I actually changed this on Blackboard, so that's a little bit mind-numbing why it's still here. This one actually should be for, as a pure substance, dipole-dipole. Oops. Let me do this one again. I did change that earlier, so I think Blackboard might be reverting to an older copy. So if you already downloaded this, please be changes to dipole-dipole. Let's go down to here. Amines are basic. So again, circling this one right here. Here we see it bonding with water, forming the ammonium. If we were to sit there and, yeah. So if you take a look at the rest of this, these also show amides, and amides will be addressed in the next commentary in the amide section. So let's go to amide reactions. If you take a look at the top part for amine reactions right here, I try to color code it, showing the hydrogen and ammonia coming together, forming the ammonium, and then the leftover hydroxide. Over here we have the amine salt formation, forming the methylammonium chloride. So let's go ahead and go back. In general, amine salt properties, if you were to sit there consequently and add in an acid, it likes to protonate the nitrogen, or to protonate the amine, forming the ammonium ion. And it will be stabilized in the amine salt form with the extra Cl. If, however, you were to sit there and add a base, it would cause it to be neutral. So let me say that one more time. Here we have the amine. If I were to sit there and add in an acid, it would force it into its ammonium state. Keep in mind, when it's in its ammonium state, it becomes really ionic, and it becomes highly, highly soluble. However, if you were to sit there and add a base, any type of base, such as maybe sodium hydroxide or potassium hydroxide, it will revert it back into its neutral amine state. And in its neutral state, it's hydrogen bonding. Keep in mind it's going to be a little bit less soluble, still soluble because it's hydrogen bonding, but less soluble than in its ionic form. That's one way that we can control the recrystallization method when we want to separate out an amine substance from another. We simply acidify it to make it more soluble, and then we can extract out the solid impurities, and then we can add a base in order to extract it out. So let's go ahead and take a look at this bottom one, quaternary ammonium salts. I didn't talk about those too much, but this is an example of a quaternary ammonium salt, AK. So FYI. So that's a quaternary ammonium salt. Why is it quaternary? Because technically this nitrogen has 4 bonds, 1 to a hydrogen, 1 to a hydrogen, 1 to a hydrogen, and to the methyl. Now, charge-wise, it's not very stable. It has an overall positive charge, which is why we need the negative charge to balance it out. Because we have positive and negatives that make it up, we call this a salt. Let's go ahead and move forward. Amines are found in neurotransmitters. So in this case, whenever you have 2 neurons And here we see their, and this is out of my field of expertise, but here we see, if we were to sit there and close this up, these are called synaptic terminals, where here we have one neuron and here we have another neuron. There's a nice, you can think of this as a moat, kind of like how you have a moat around a castle. Here you have a moat, a cellular moat between these two neurons. So we need a way of transferring information between these. So see these little triangles right here? Those are the neurotransmitters. So think of these neurotransmitters as boats on a moat. And they travel from one of the neurons to the other neurons. I'm not going to use the terminology for each section, but they travel from one neuron to the other neuron. And so it turns out that a lot of these special chemicals, these chemical boats that transfer from one neuron to the other, they tend to have a lot of amines present. So here are various types of amines you might find present. Here's their general characteristics, which you have to memorize. So for example, here we have dopamine, here we have norepinephrine, and here we have epinephrine. For dopamine, notice it has the amine in the name. So this is what dopamine looks like. It has a parent benzene ring, and then you have two alcohols present. And then you have a alkyl arm which comes off and ends in a amine. Now there's a ton of neurotransmitters. So what I want to go ahead and do is give you the ones you have to memorize. That means you have to sketch these. I know I'm writing messy, but I'm in a hurry. So you have to sketch these. And so notice the pattern. The pattern going from dopamine to norepinephrine is the hydroxyl group. Notice these look exactly the same. The only difference is the hydroxyl group. Now, dopamine affects various types of behavior as well as motivation. Norepinephrine is very similar, and its effects are a little bit better categorized. Feelings of elation, low levels of depression. If you have extreme amounts, then you may be in various stages of a manic state, either high or low. Drugs called beta blockers, they reduce the stimulation of norepinephrine, and with less norepinephrine, then you have less extremes in the manic state. And notice the only difference between these two molecules is the hydroxyl group. Let's go down to adrenaline. Epinephrine, aka adrenaline, has many functions. It also serves as a overall hormone, body hormone, but it can also serve as a neurotransmitter. One of the reasons I picked this one out as well is because it's very easy to see the differences. If we take a look at norepinephrine and epinephrine, notice the only difference is this extra methyl group. It's the only difference. Take off that methyl group and add a hydrogen, then you're back to norepinephrine. So the body's very conservative with its molecules and only likes to make subtle changes in order to create a brand new neurotransmitter. So let's go ahead and make sure you memorize all of these names, sketches, and general properties. Alkaloids. So these are plant drugs. These plant drugs all contain amines. This right here is a tertiary amine. 2 bonds to a carbon, 3 bonds to a carbon, excuse me. Here we have another tertiary amine. So this is what tobacco looks like. This is what caffeine looks like. And then this is what opium looks like. Notice the cool, we call this a bicycloalkane because you have a bridge that goes right across. I always thought that was cool. So um, a lot of stuff to do. So in this part, all you have to do is recognize. Do not sketch these, but simply recognize them and give the names and give their overall properties. Um, and that concludes this set of slides in a nutshell.